I heard Bean Kim speak at the KDD conference in 2019, where she impressed everyone by her work around interpretability of artificial intelligence. I knew this topic would be of great interest to the WiDS community, and we were all delighted that Bean agreed to speak at our conference last year. This talk from WiDS 2020 was definitely a highlight. Bean shared an overview of where we are today with interpretability, where she believes the field is heading, and also a bit about her work at Google to improve interpretability of AI using post-training interpretability methods. Enjoy.
Thank you. Thanks. Hi. I love speaking to a room full of talented women. There's just something about it. You know, we can talk about research, which I'm gonna do, but we can also talk about imposter syndrome, which I very much resonate. So I hope that you've been enjoying today, networking and appropriately sanitizing your hands whenever necessary. So today I'm going to talk about a little bit of research that I do at Google, interpretability for everyone. The research in interpretability last couple of years has been amazing. A lot more papers were published, unlike when I was doing my PhD, a lot of workshops. But I still see this as a drop in the ocean because interpretability has all these complexities that all machine learning folks already have, plus complexity of humans. It's so complex that we have a whole field just dedicated to humans. It's called psychology. And perhaps that's why people keep being interested in this topic, but that's also why we have to think about where we're going. There's so many directions we can go, but we as a community have to row in the same direction so that we can go somewhere in a couple of years. Otherwise, we'll be rowing in all sorts of directions and rotating in circles all day. So today I'm going to talk about, first, where are we going? And second, taking a critical look at the toolkits that we already have that would help us point where we should go next. And then I'll suggest an idea that might be slightly better. And then we're going to come back to that idea to criticize that very idea, to inform us, help us think about how we can do even better. And then I'll finish with what we should be careful in general in our journey. So first, where are we going? Unlike supervised machine learning, which we have accuracy, which is a flawed metric, but generally we roughly agree, okay, that's roughly where we should head to. But interpretability is a little different. Because we have humans involved, humans, you can't really define anything mathematical about humans, well, at least not yet. So we don't have that clear goal. And that requires us to ask a harder question, a value judgment. What are you trying to achieve ultimately, and what are your values? Now, your goal and your values are yours, but I'd like to share my goal. My goal is to help people use machine learning more responsibly and more effectively. And that could mean a lot of things, but one, it means to me that we can align our values in the model, and our knowledge can be reflected when we want it. And I particularly care that this can be available for everyone for two reasons. One, for high-stake domains like medical, we have doctors who may have domain expert knowledge that is critical to make important decisions, but they may not know machine learning. But those are the cases where interpretability becomes most useful and important. And second, machine learning is a powerful tool, and it shouldn't be the case that you're lucky enough to be educated in computer science or math to be able to leverage that powerful tool. I think everyone deserves to leverage that powerful tool. And that requires being able to understand how it's doing and being able to build on top of that. It's important to think about what are not our goals. It is not about making all models interpretable. So models, it's overkill. You don't need interpretability. It's also not about understanding everything about the model, because the ultimate goal is, remember, reflecting values and reflecting your knowledge. And that might just be, the saving some more patients or debugging this one bug. And that does not always require understanding everything about the model. Not about against developing highly complex models. And perhaps most importantly, it's not just about gaining trust. In fact, if the model does not deserve to be trusted, the interpretability method should reveal that. For example, this beautiful paper came out last year that showed that deep learning model that predicts hip fracture pretty well wasn't actually looking at the medical image at all. It was looking at X-ray or whatever the medical machine that was taking the medical picture and the model number. Some models are older than others, and perhaps it reflected some where the hospital was and economic status of that area. An interpretability method did the right thing. It revealed that this model isn't reliable, shouldn't be trusted. So next up, what do we have now? So today, there are lots of different interpretability methods, but I'm gonna focus on one specific type, and it's called post-training interpretability method. What does that mean? That just means that somebody gave the model to you, and you can't change the model, and you're gonna do the best in interpreting that model. So for example, you might have a model that takes a picture and predicts what's in the picture, in this case, a bird. And the goal of interpretability method is to explain why was this a bird. One of the most popular method in interpretability is called saliency map. How many people heard of saliency maps? All right, no worries. It is using a first-order derivative to test if I change this pixel a little bit, how much would the probability of bird change? Because intuitively, if we change this a lot, it's an important pixel. If it doesn't, it's not an important pixel. That's the basic idea. It's very popular. So the promise of this method is that this is the evidence of prediction. These are the pixels, why it was predicted as a bird. Then we can ask a sanity check question. Okay, well, you said it was evidence of prediction. So if the prediction changes, then the explanation should change. In fact, we can make this really extreme and make the prediction completely random, a garbage network. And in that case, the explanation should really change. So we test that. So here's the network beautifully trained, high performance. We got a bunch of images and we got a bunch of explanation, the saliency map, which would look like this. And then we copied that network and we randomize it from the last layer, the prediction layer, all the way to the bottom layer. So this network is garbage. It does not predict, it predicts randomly, okay? So you would think that explanation should change. It doesn't. And you might think that, well, come on, these are technically different pictures. They did change a little bit. But remember, the final consumer of interpretability method is a human. And as a human, I don't think I will conclude different things looking at these two pictures. The belly of the bird, still important. The cheek part or the head part of the bird looks still important. So we did this for many methods. Each row is different method, one of which is my own work. And we cascading manner randomize each layer. So the last column, you're looking at completely random network. And as you can see, some method doesn't even change. So in this paper, we also calculated quantitatively rank correlation and other things to show that in numbers too, this is true, which is quite shocking. So we were very confused and shocked, and in fact, community was. So how did this happen? Confirmation bias. This is such a strong thing that it's just weird being human. We were given a bird picture. We expected to see a bird. We saw a bird, and we liked it for years, and myself included. Is this something that we as a human just have, and we have to take that into account when we are designing an interpretability method. Folks in the same time, reached the similar conclusions. Some folks mathematically proved that some of these method just looks at the picture and not at all the prediction. But some work show that when shown these explanations, humans did better in a final task. So maybe there is something, we just don't know what it is yet. We need to do more study what that is to get more of that. So how can we do better? So we're still thinking about the same problem, which is a subset of interpretability method. And now I took a cash machine picture, and again, the goal is to explain why was this a cash machine. Let's get that saliency map that we just talked about to help us think about what do we really want to ask when we look at an explanation. So I squint at this picture, and I see this human in front of the cash machine a little highlighted. So I start thinking, oh, maybe it makes sense. Cash machine maybe often have a human in front of it. But for odd reason, the wheel behind the human is also highlighted, which is a little concerning. Then I start wonder, well, did these concepts matter, or am I seeing just illusion? If they do matter, then which one mattered more, and did it matter for all pictures or just this one picture? The problem is that pixel-based method, you can't quite express this concept across many pictures, like humans. And you would have been fine if you had this concept as a part of an input feature, then you get the weight and you're done, but you didn't. I just made it up. After the model is already been trained, you can't change the model. So we developed this method called TCAV, testing with concept activation vectors, which is the goal to give a quantitative measurement of a concept or concepts that you came up with after training, if and only if it mattered. It will be obvious and why that is the case. So I'll explain to you how this works. This is pretty relatively simple method. And I'm going to use a zebra. You have a classifier that predicts a zebra, and you're wondering whether a stripeness pattern mattered for that prediction. So first and foremost, you might ask, okay, well, concept sounds good, but what is it? Like, how do you even express what that is? Well, we do the simplest possible thing. We represent that concept as a vector. And this has been done before. How do we do that? Well, you get some examples of that concept that you're interested in investigating, in this case, some stripeness pictures, and you get some random images. And you have a network that you want to investigate. Then what you do is you simply get a linear classifier that separates random activations from concept activations, and get a vector that is orthogonal to the decision boundary. What is that vector? Well, it's just a vector in the embedding space that points from random stuff to your concept. That's all there is. So you have this vector that represents the concept. Next is to get that quantity, or the TCAV score. How important was this concept? Also pretty simple. We are going to take what's called directional derivative. This is, intuitively speaking, if I take this zebra picture and make it more like the concept, how much would the probability of zebra change? If it changes a lot, it's an important concept. If it doesn't, it's not an important concept. It's basically it. Then we do this for many, many zebra pictures and calculate the ratio of zebra pictures that gave you positive directional derivative, which just means that having the concept increased the probability of zebra. So you had 100 zebra pictures, you calculate derivatives, and 80 of them came out positive, then your TCAV score is 0.8. So that's not all. Super quickly, we have a way to quantitatively validate that this is not some spurious CAV, because we all know that in high embedding space of neural network, funky things happen, like adversarial examples. So here's one way we propose to confirm that. The basic idea is that you get many, many concept vectors using many, many different random sets of examples from which you get TCAP scores, and pretend that that's a sample, there are samples from a particular distribution, and do statistical testing on that to distinguish that from TCAP scores from random CAPs, where random CAPs are just random versus random pictures. So it's just confirming that this is at least better than random concept on this particular class zebra. So some results, I have a lot of my favorites, but I'll just talk about this medical example. Diabetic retinopathy is a medical condition that is treatable but sight-threatening condition. At Brain, we have a model that can accurately predict DR. But our question is, well, would doctors do the same thing? Does the concept doctors use same as the model used? So we went to a doctor and we asked her which concepts she expects to see at a particular level of DR level 4, that's the most severe level of DR, and what are the concepts that she does not expect to see for that level, and similar for lower level of DR. Then we asked the model with TCAV, what do you think? It turns out that when the model accuracy was high in the DR level 4, model was using concepts that doctors would have used. So that's cool. But when model accuracy was mediocre, the model was using something that doctors did not expect, which is the HMA. It's a type of hemorrhage in your blood vessel. And they went back and realized that the DR level 1 and 2, the doctors were labeling all over the place. And in fact, this HMA appeared a lot in DR level 2, which was often confused by the model with DR level 1. So they went back and revisited the labeling process. I've been lucky to observe a lot of passionate responses from academia on this work. Carrie Kai had this Kai conference paper. They used CAVs to concept activation vectors to help doctors sort through medical images. So this time doctors are looking at images not as in terms of pixels, but in a language that they're familiar with, medical concepts. I met Eric, who used TCAV for storm prediction. Mara used this for breast cancer and a lot of other things, MRI from King's College, and so on. And I was also really lucky to see that Sundar talked about this work at Google I/O 2019. My dad was very happy. I think he stood up all night to just watch this. And this work was also won UNESCO NetExplo Award, which is given to 10 digital innovations, and I quote, that will potential profound and lasting impact. So let's come back to what we just talked about. How can we do better? Plenty of permutations of TCAV that I think we can, this is such a simple framework that we can all extend and people have. One, concepts has to be expressible using examples. So something that overlaps a lot in your images or something that cannot be expressed using examples, you can't really use this. You need labels of concepts. We proposed an idea last year about how automatically do this for images, but we don't know how to do it for language, for example. Or making it causal. All these are that I talked about so far is correlation based. It's not causal. So we propose an idea, but you still need to train a generative model, which correctly reflects the data generative process, which is hard, and causal is always harder. But there's a lot more work that we need to do. Finally, I want to talk about what we should be careful in our journey. Proper evaluations. I cannot emphasize this more. So remember I talked about the complexity. Because we are so complex, it is very hard to tease out what we like versus what's true. And it requires a lot of thinking. And you can perhaps achieve that by doing some sort of sanity check that I did, or crafting a data set where you know the ground truth, what is important, and confirm that. It can be toy data set. It's just sanity check ourselves. Testing with humans. Remember, nothing we're doing is useful if it's not consumed by humans. So we have to check with humans that it works. Remember, we are beautifully human and biased and irrational. In fact, if you're into reading, I highly recommend Danny Kahneman's book on Undoing Project, where he beautifully describes all different biases we have, example by example, like statistical quizzes that you can attempt to solve, and I failed a lot of them too, because you're just biased, even in given like facts and numbers where you can calculate them. HCI, I think a couple of folks had talked about this already. I cannot also emphasize enough importance of HCI. We have to think about workflow. It's not just about math and algorithm. We have to think about interfaces. We have to think about how humans respond, human studies, human factors, psychology, cognitive science. These things all have to come together to make this work. And let's keep checking that we're going to the right direction as we go, so that in many years, hopefully not too long, we can sit somewhere and say, we've come here because we all row into the same direction. Thank you so much.